Welcome everyone to the lecture that was supposed to occur at 8 a.m. on Thursday, October 28th. I'm posting this one as a video so that we don't have to make major changes to the course schedule. Today we're going to be covering the first part of Chapter 8, Sections 1 through 4, and it will begin our unit on rotational motion. This whole chapter is going to have a lot of equations that we're going to write down, but the good news is that they are all related to equations that we already know, and it's just couching them in terms of rotation instead of in terms of linear motion. So we'll have a lot of similarities here. For example, we had the linear position that was x and was measured in meters. And the linear position was all about where an object was located along some axis. We'll now have the equivalent rotational variable of this, the angular position, which will be theta, and it will be measured in radians. Radians may be the SI unit for the angular position, but sometimes these values will be given to you in different units. They could be given to you in terms of the number of revolutions or the number of rotations, or in terms of how far the object rotates in terms of degrees. So some conversion factors might be helpful here. One revolution or one rotation is equal to 360 degrees, which is equal to 2 pi radians. And you can use this conversion factor to get your values into SI units before you plug them into your equations. So what this linear position and angular position is getting at is a new way of measuring position in terms of rotations. So the angular position doesn't care how far you moved in terms of meters, it's just all about what direction the object is facing and assigning an angle to denote that position. We can relate these two variables by some sort of equation that will basically be a conversion between the linear position and the angular position. And that relationship is given by L equals R times theta. So what this means is that if we have some object that is, say, on a rotating platform like a merry-go-round, then we could specify that object's linear position in terms of x's, y's, and z's, but if we want to specify its angular position, then we want to give some angle at which that object is facing. And if this object then moves, for example, it moves later as this table rotates to this position here, the object will have moved through some angle theta. So this angle theta is the angular distance, the amount that our system has rotated. Could be given to you in degrees or radians or revolutions, but we'll want radians for our formulas. And how this relates to L is that L is the distance the object would actually move as this table rotates. So this distance right here in blue would be L. And then the only other variable involved here is R, which is some sort of radius, but just to define this very, very clearly, in all of the equations we'll have today for going back and forth between linear and angular quantities, R is the distance between the object and the axis of rotation. So we could use this to relate the distance that object travels to the number of degrees or number of radians the object rotates. So I'll do a quick example here to show you what I'm talking about. Let's pick some numbers for this setup that I have down at the bottom, and we have an object that is, say, 0.8 meters from the center of this merry-go-round, and as the merry-go-round rotates 110 degrees, how far did it actually travel? So this question is all about relating an angular distance to a linear distance. And that's what the equation L equals R theta is all about, and that's the equation that we're going to be using here. So L is what we're trying to find, the linear distance that the object moves. R is the distance between the object and the axis of rotation. So in this problem, that's pretty clearly 0.8 meters, but try not to get fooled by different distances or different radii being given in a problem. For this problem, for the merry-go-round I've drawn, the radius of the merry-go-round is not the same thing as the distance r that we need. R is the distance from the center of the merry-go-round's rotation from that axis to the object itself, and the object is not at the edge of the merry-go-round. So we only need that 0.8 meters. And then theta, the amount that this system has rotated, was given to us as 110 degrees. But the SI unit for angular position or angular distance is radians, not degrees, so we'll have to do a quick unit conversion here. So following the normal rules of unit conversions, I want to cancel out the units of degrees, which are in the numerator, so I'll put degrees in the denominator. I want to replace it with units of radians, so I'll put radians in the numerator. Now I just need to find numbers to plug into this conversion factor so that the top equals the bottom. And from the conversion factor I showed you all just a little bit ago, we can see that 2 pi radians is equal to 360 degrees. We can multiply across the top and divide across the bottom in order to get the value for theta that we need in radians. And we get a value of 1.92 radians. So now we're ready to plug in. L is the distance of our object from the center of rotation, 0.8 meters, times the amount that that object was rotated in terms of radians, so that 1.92 radians. We multiply those together, and we get an answer of 1.54 meters. So this is a distance that we asked for, so it makes a lot of sense that our answer is in meters, but if you're paying attention to the units I plugged in, you might be asking yourself a question right now. We just multiplied a value in meters by a value in radians. So what happened to the radians? Why is my answer not in units of meters times radians? And this brings up something about radians as a unit that I want to talk about that's important to understand. Radians is not a real unit, not in the same way that meters and seconds and kilograms are. Radians is, I describe it like Batman sometimes. It appears when it's needed, and when it's not needed anymore, it will disappear into the night. So as we've effectively converted from a linear, or from an angular distance to a linear distance here, we started off with radians, but because we've just calculated a linear quantity, the radians will just disappear into the night, and we'll be left only with the meters as our answer. So let me write that down, or at least a summary of it. So pretty straightforward so far. The distance L in that previous problem is known as an arc length, and there are other ways to find it, but that equation in green is the one that we're going to be using. And now that we've talked about angular position, we can start to talk about our next angular quantity, which is the angular velocity. So linear velocity was v, and was defined as the change in position over the change in time, and was measured in meters per second. Angular velocity, on the other hand, will have the variable of lowercase Greek letter omega, and will be defined as the change in the angular position over the change in time, and will have units of radians per second. As before, we will have an equation that will relate the two of these, and it will have the same form as the equation that relates the linear and angular positions, or linear and angular distances. It will be that the linear one is equal to r times the angular one. So in this case, that is the linear speed, or the linear velocity v, is equal to r times the angular velocity or speed omega. So these equations in green will turn out to be pretty important because they are how we go back and forth between linear variables and angular variables. The linear velocity is all about how fast something is moving. What a cop's radar gun would measure is the linear velocity. Angular velocity is all about how fast something is rotating. So the faster it rotates, the higher the angular velocity. And it doesn't really matter how large the object is or how small the object is. A merry-go-round rotating at 5 revolutions per second has the same angular velocity as a CD on a CD player rotating at 5 revolutions per second. Just like linear velocity can be measured in a bunch of different units, miles per hour, meters per second, inches per year, but we only have one SI unit, meters per second, angular velocity can also be given to you in different units, but we will always need to convert to radians per second if we want to use one of our equations. Some common units of angular velocity that you might be familiar with is RPMs, which is revolutions per minute, or rotations per second, or even degrees per second or degrees per minute. But the most common one most people are familiar with is RPMs, or rotations per minute. So with the conversion factors we already have, you could take the RPMs of your car's engine and convert that into the SI unit of radians per second. I've also shown omega as a vector, and angular velocity technically is a vector, and I don't want to get too far into the weeds about exactly how we determine that. It's related to something called the right-hand rule that we will spend some time talking about next term, or you'll spend some time talking about in the second semester of this class. For me, it's enough to know that if an object is rotating counterclockwise, then the angular momentum or the angular velocity points out of the page straight towards you, and if an object is rotating clockwise, the angular velocity points into the page or directly away from you. This is basically a side note because I don't plan to get into the vector nature of omega in any great detail in this course, but it's important for one part of a homework question that I otherwise like a lot, but you'll need to know what I just wrote down in purple in order to answer one of the parts of that homework question. For the most part, when we think about the direction or the sign of angular displacements, angular velocities, and later on angular accelerations, we'll use a different kind of coordinate system where we think of clockwise and counterclockwise as being our negative and positive directions. And normally I will take counterclockwise to be positive. The coordinate system I will use and draw on a lot of problems looks like this, with an arrow just making a counterclockwise circle and a little positive in the center of it. And this tells me that anything counterclockwise is positive and clockwise is negative. And that will turn out to be important when we get to the rotational kinematic equations a little bit later on. But before we do that, I want to do a conceptual question, kind of clicker style, and then do a couple of calculations related to that. So, let me get that set up. So we have two people standing on a merry-go-round, and that merry-go-round is rotating counterclockwise at a rate of 2 revolutions per second. The blue person, which is the person closer to the center, is a distance of 1.5 meters from the center of the merry-go-round, and the red person is a distance of 3.0 meters from the center of the merry-go-round. The merry-go-round itself has a radius of 3.8 meters. So eventually we'll do some calculations with this, but before we do that, I want to start with a couple of clicker questions. So I'll get those written down. So pause the video right now and take a minute to think about this and see if you can come up with what you think is the correct answer. And then once you're done, unpause the video and we can discuss what the correct answers are. All right, hopefully you took the time to pause the video and figure out which of these 2 or 3 answers you think is correct. First, let's look at which person has the larger linear speed. Linear speed is the amount of distance that a person covers divided by the amount of time it takes them to cover that distance. This blue person is moving around in a circle, and they will have to cover that full distance, the circumference of this blue circle, in 1 full rotation, however long that takes. At 2 revolutions per second, that would be half a second it takes to cover that distance. The red person, on the other hand, also takes half of a second to make a complete revolution around this merry-go-round, but they have a much larger distance to cover. So even though they're making both 1 revolution, the person in red is making a bigger circle in the same amount of time, so the red person will have the higher linear speed. Let me do a calculation to show you what I'm talking about here. So linear speed is distance over time, and each of these people, let's look at 1 full rotation, is traveling a distance of 1 circumference of a circle. So d for our red person is 2 pi r, and the r we need here is the radius of the circle that the red person is making. So we want, let me do that one in red. So we want this r for our red person. That is not the radius of the merry-go-round, it's this 3.0 meters. The distance of that red person from the axis of rotation will define how big the circle they make is, which will define how far they travel. So plugging in, we have 2 times pi times 3 meters gives us a linear distance of 18.85 meters. And then we need to figure out how long it takes this person to cover that distance. So this was the distance for 1 full rotation, and if we have 2 revolutions per second, that means we're going to have 1/2 of a second for each revolution. So the t here we'll find by taking 1 over the rate of rotation. So 1 over 2 revolutions per second is 0.5 seconds per revolution. But revolutions is kind of like radians in terms of a unit. It can be helpful for thinking about our unit cancel, but it's not a real unit, so this is really just 0.5 seconds. So to find the linear speed of the red person, we can take that distance, that 18.85 meters, and divide it by the amount of time it takes to go that far, 0.5 seconds, to get our linear speed of 37.7 meters per second. And we can do the same thing for the person in blue. The distance they have to cover will also be 2 pi r, but this time we want the radius of the circular path the blue person is making, which is going to be this distance right here, which turns out to be the 1.5 meters. So we've got 2 times pi times 1.5 meters, which gives us an answer of 9.42 meters. The time here is the same amount of time as before because it will take this blue person the same 0.5 seconds to complete that 1 rotation. And that should give you an idea what the correct answer for the second clicker question is, but let me finish this calculation first. The speed then is that distance, the 9.42 meters, divided by the 0.5 seconds it takes the person to travel that far, which gives us an answer of 18.8 meters per second. The other clicker question we had was about which person has the larger angular speed. And angular speed is all about the number of rotations you make in a given amount of time. The number of radians traveled, the number of degrees, but you can think of it in terms of rotations. It takes each of these people 0.5 seconds to make one complete revolution or one complete rotation. So as the merry-go-round rotates once around, both of those people move through an angular distance of 2 pi radians. So that means that they will both have the same angular speed. So this problem is really good at driving home that difference between the linear speed and the angular speed. Linear speed is how many meters you cover per second. Angular speed is how far you rotate per second. So if we have our linear speeds, we also have our angular speed because we know r. So we could calculate our angular speed easily enough here for both of them, which we could calculate by just converting this 2 revolutions per second. The angular speed that they both share is 2 revolutions per second, and if we want that in SI units, we're going to have to convert revolutions to radians. So 1 revolution on the bottom, 2 pi radians on the top, gives us a value of omega that is 4 pi radians per second. And since this is rotating counterclockwise, if I take my normal coordinate system, this would be a positive 4 pi radians per second, which in regular old decimal form works out to be 12.57 radians per second. Again, positive because it's rotating counterclockwise. We could also determine the radians per second here by using our relationship between our linear and our angular variables. So we could use v equals r omega, which could be rearranged to tell us that omega is equal to v over r. So for the red person, for example, omega would be equal to the speed of that red person, 37.7 meters per second, divided by the r for that person, which was the 3.0 meters, which gives us an answer of that same positive 12.57 radians per second that we got the other way. So this is just another way to determine the same thing. And again, I want to draw your attention to what happened with radians here. There is no radians that is plugged in to this equation. We have meters per second divided by seconds, so that should cancel out the meters and leave you with just 1 over seconds. But we need to remember that radians isn't a real unit, and we've just converted from a linear speed, 37.7 meters per second, to an angular speed, 12.57 radians per second. So because we've gone from a linear quantity to an angular quantity, the radians pops up here because it's needed. We've talked about position, we've talked about speed and velocity, so the next thing we're going to talk about is the angular acceleration. As before, we will start our discussion by talking about linear acceleration, which was the variable a and was defined as the change in velocity over the change in time and was measured in meters per second squared. Perhaps not surprisingly then, the angular acceleration will be given by the variable alpha, lowercase Greek letter alpha, and it will be equal to the change in the angular velocity divided by the change in time, and will be measured in radians per second squared. And again, we will have an equation that relates these two variables, that the linear acceleration is equal to the angular acceleration times r, the distance of the object from the center of the circle. But there's a slight difference here. This is just going to be the tangential acceleration. And to really define what that means, I need to go back to chapter 5 when we talked about the centripetal acceleration. For an object moving along a circular path, we have kind of two different components of acceleration that we think about. And we've seen one of these before. We had the centripetal acceleration, which was the component of the acceleration that points towards the center of the circle. The centripetal acceleration was all about the direction of travel changing, but not the speed changing. Remember, in uniform circular motion, the speed was constant. We knew the centripetal acceleration always pointed towards the center of the circle, and it had the formula v squared over r, and we'll have a new formula for the angular acceleration if we want to, by changing that v over to an omega, using that relationship between linear and angular speed. You can also define the centripetal acceleration as omega squared times r. Now we have a new component to our acceleration, and this is the tangential component to the acceleration, tangent to the edge of the circle, so this is a tan. This is the one in the equation that I wrote down before in green. The tangential acceleration is all about the speed changing, but not the direction of travel. So the tangential acceleration is about the speed of the object changing, and the centripetal acceleration is about the direction of the object's velocity changing as it moves in a circular path. And if we combine the two of these together as vector components, we get the overall acceleration. So the overall acceleration of this object would point in the direction of this blue arrow that I'm drawing here. And since that acceleration has both a centripetal component and a tangential component, its speed will be changing, and it will be traveling along a curved or circular path. And we could find the magnitude, then, of the acceleration the object is experiencing by basically combining our vector components here using the Pythagorean theorem. The centripetal acceleration squared plus the tangential acceleration squared. I don't plan to hit this idea very hard on tests or quizzes, but it's important that you understand that this acceleration right here is not the overall acceleration. It's just the component of the acceleration that's actually affecting the speed of the object. I have just a couple more equations that I want to put on the board that can be helpful here and there before I start to get to kind of the meat of what we're going to talk about today. One of them is that you will sometimes see an object's rate of rotation given as a frequency in hertz. When an object's rate of rotation is given as a frequency in hertz, you can basically think of that as revolutions per second. So that means if you're given a frequency in hertz, you will need to convert that over to an angular velocity in terms of radians per second. This basically just amounts to a unit conversion between revolutions and radians, but having the equation can be helpful. Do be careful when plugging something like this into your calculator. You will need parentheses around your denominator in order for order of operations to give you the answer you actually need. The other variable I want to define here is capital T, the period, which is the amount of time it takes for the object to complete one full rotation. Since this is a time, it will have SI units of seconds. And the period is related to the frequency by an inverse relationship. So the period is equal to 1 over the frequency. So again, those aren't kind of the main conceptual points I'm going over here. That's the definition of these new angular quantities and how they relate to our linear quantities that we already know. But these equations can be helpful for solving some problems. I want to start to drive home a point that I hit pretty hard in these topics, which is the idea of what I call sister variables. All variables that we have in basically every equation we've learned so far this term have an equivalent variable in terms of rotation, and I call that pair sister variables. So for everything we already knew for linear stuff, we will have an equivalent in terms of rotation stuff. And often we will have some sort of equation that relates the two. So for example, we had the linear position or linear displacement or linear distance delta x. And we talked about its angular equivalent, its sister variable, the angular distance delta theta. And we had a relationship between the two of these, which was that the linear distance equals r times the angular distance. This is the first time the deltas are appearing. When we think about distance or displacement, we want to know how far an object moves, so it's just the change in the position, whether angular or linear. And then we had the velocity or the speed. The linear speed was v, and our corresponding angular speed we called omega. Suppose I could put some units on these. Linear distance is in meters, linear speed is in meters per second, and angular distance is in radians, and angular speed is in radians per second. But as with the angular and linear distance, the angular and linear speed had a relationship. V equals r omega. Linear equals the radius of the circular path the object is following times the angular quantity, omega. Then we had our linear and angular accelerations. The linear acceleration being in meters per second squared and the angular acceleration in radians per second squared. And again, we had the relationship. Linear equals r times angular, but we have the extra little caveat here that it is the tangential acceleration only that we're talking about. But this kind of one-to-one comparison between linear variables and angular variables isn't limited to just individual variables. Entire equations will have rotational equivalents, including our next topic, the kinematic equations. So our kinematic equations, at least the first one of them that we learned, was Vf equals Vi plus At. The final linear velocity equals the initial linear velocity plus the linear acceleration times time. And to find the angular equivalent of this same equation, we just need to take all of these variables and change them into their sister variables in rotation land. So instead of final linear velocity, we'll have final angular velocity equals initial angular velocity plus the angular acceleration times t. T does not have a rotational equivalent. It works just as well in linear land and rotation land. Our next kinematic equation, Vf squared equals Vi squared plus 2a delta x, then becomes omega final squared equals omega initial squared plus 2 times alpha times delta theta. And last but not least, the quadratic kinematic equation, delta x equals Vit plus 1/2 At squared, becomes delta theta equals omega initial times t plus 1/2 alpha t squared. So we can use our rotational kinematic equations in a similar way that we used our linear kinematic equations. And I want to go over this idea in an example problem or two to really drive this point home. It will feel like we've just learned a whole new set of equations, but it's really the same ideas, the same process that we used before, just with rotational variables instead of linear variables. So we have a bicycle that has wheels of diameter 0.66 meters, and it's slowing from 7.5 meters per second to rest over a distance of 52 meters. And we're asked to find the angular acceleration of the wheels and how long it takes the bike to stop. So this feels like a kinematics problem, except for the fact that they've asked for some sort of angular variable and we have something rotating, which is the wheels of this bicycle. The most important part to understand about a kinematics problem like this that has mixed variables between linear and rotation is that you need to pick a lane and stay in that lane. You need to either work with all linear variables and all of your linear equations, or all rotation variables and all of your rotation equations. Since we are teaching you all how to use rotational variables, let's convert everything over to rotation land and do our calculations there. So we were given an initial velocity, VI, of positive 7.5 meters per second squared. If we take the direction of travel to be positive, 7.5 meters per second, and we want to convert this over to an angular variable. So we want to make this into omega I. And omega is equal to V over R. So omega initial equals V initial over R. Our initial our initial linear speed velocity was that positive 7.5 meters per second, and we want the radius of the thing that's rotating. For an object that rolls without slipping, the value you need here is the actual radius of the object. So that's half the diameter, so we need 0.33 meters, and we have an initial linear velocity of positive 22.7 radians per second. Note that this is a situation where we've converted from a linear quantity to an angular quantity, so that means radians as a unit will pop up because it's needed now. We can also find the final angular velocity by the final linear velocity divided by r, and this just turns out to be 0 radians per second because the final velocity of this object is 0. We then also need to take this 52 meters and do something with it. That 52 meters, positive 52 meters, is our delta x, and we need to turn this into a delta theta instead. Delta theta is delta x divided by r, so that is the 52 meters positive that our bicycle has traveled, divided by the 0.33 meters of the radius of the rotating object, which gives us a value of positive 157.6 radians. You can do a quick unit conversion here to show that this is equivalent to 25.1 revolutions, which means the bicycle wheels completed just over 25 complete rotations before the bicycle came to a stop. Just like the regular kinematic equations, we follow the same process for the angular kinematic equations, and we have found 3 variables, omega initial, omega final, and delta theta, and we're looking for angular acceleration alpha. So we can go equation hunting and see that we need omega f squared equals omega initial squared plus 2 times alpha times delta theta. And we can then plug things in here. So we've got our final angular velocity is 0. Our initial angular velocity was that positive 22.7 radians per second squared plus 2 times alpha times our delta theta of positive 157.6 radians, making sure to plug everything in radians per second, etc. And if we solve this, we get an answer of negative 1.64 radians per second squared. The negative here means much the same thing it did with linear acceleration. For linear acceleration, if the velocity is positive, then a positive acceleration meant speeding up, a negative acceleration meant slowing down. Or if the velocity was negative, a negative acceleration meant speeding up and a positive acceleration meant slowing down. Since we have a positive angular velocity in this problem, and we got a negative angular acceleration, that means our velocity and our acceleration have opposite signs. So this object must be slowing down, which makes sense. We could also then find the amount of time it takes with omega final equals omega initial plus the angular acceleration alpha times t. So that's 0 equals our positive 22.7 plus our angular acceleration we just found, that negative 1.64 radians per second, times t, allows us to solve for t, which is 13.8 seconds. That is the amount of time it takes this bicycle to come to rest. This is one way to do this problem, but it's not the only way. We picked our lane of rotation land and we stayed in that lane the entire time, converting all of our variables over to angular quantities. But another option here is to do all of our math in linear land and then just convert over at the end. We're asked to find the angular acceleration, alpha, so first we could find the linear acceleration and then convert that over to its equivalent angular variable. So we could, for example, use vf squared equals vi squared plus 2 times a times delta x. And that would give us 0 squared equals positive 7.5 squared plus 2 times our acceleration times the 52 meters that we have. And solve for our acceleration, which is our linear acceleration, negative 0.541 meters per second squared. We can then say that we know our angular acceleration is equal to our linear acceleration divided by the radius. So we take that negative 0.541 meters per second squared, and we divide it by our radius, that same 0.33 meters from before, and we get an answer of negative 1.64 radians per second squared. We've just solved for an angular acceleration, so we expect radians per second squared, but note again that we've just gone from a linear value, acceleration, to an angular value, also acceleration, so radians just pops out of the woodwork. We could have also solved for that time without using any of our rotational equations at all, with Vf of 0 equals Vi of 7.5 plus our acceleration of negative 0.541, because we want the linear acceleration in this equation, times t, to get that same time of, this time we get 13.9 seconds. They're only different because of some rounding issues, because I rounded my intermediate steps on this problem. But we can do this either in linear land or in rotation land, as long as we pick a lane and we stick to it. So let's do one more problem here and see what we think about it, and then move on to our last topic for the day. So we have a ladybug that is sitting a distance of 0.8 meters from the, 0.08 meters from the center of a record that has a radius of 0.15 meters. The record is spinning clockwise at 45 RPMs, but slows to 33 RPMs over the course of 1.8 seconds, and we want to find the angular acceleration of the record. I'm going to take counterclockwise to be positive for this problem, and before we get to the calculation here, I want to ask you a clicker question. Is the angular acceleration going to be positive, negative, or 0? So again, go ahead and pause the video to think through this one and see if you can figure out the answer. Then unpause the video to check. So hopefully you have yourselves an answer, and for this problem, our record player is slowing down, which tells us that the acceleration will be opposite the direction of the velocity, just like with linear values. But our record is spinning clockwise, so this tells us our angular velocities are going to be negative, which means for the object to be slowing down in its rotation, the angular acceleration needs to be in the opposite direction, or the positive direction. So let's go through the math here now. We have our initial angular velocity is given to us. as 45 RPMs, which is just revolutions per minute. And this is in the clockwise direction, so this is a negative value. So this is an angular velocity, but it's not in the units we need for our equation, so we're going to have to convert. So we'll have to convert that minutes to seconds by dividing by 60, and we will have to convert that revolutions into radians by multiplying by 2 pi. And when we do all of that, we get a value of negative 4.71 radians per second. And we're going to have to do the same thing with the final velocity as well, because our final angular velocity is negative 33 RPMs, or revolutions per minute. And we end up with a value of negative 3.46 radians per second. We know that t, the amount of time it takes this deceleration to occur, is 1.8 seconds, and we are looking for the angular acceleration alpha. So we go looking for an equation that will help us. Omega final equals omega initial plus alpha t, and we plug in the values that we have. The negative 3.46 radians per second as our final angular velocity. The negative 4.71 radians per second as our initial angular velocity. And the 1.8 seconds as our time. And then we solve for alpha, and we get an angular acceleration of positive 0.694 radians per second squared. This should give you a decent idea how the angular kinematic equations work, and you'll see a few of those problems on your homework as well. Some other things you'll see on your homework this week will be the next topic we're going to cover, which is torque. So let me clear the screen and we will start the next and last part of our lecture for today. When we reached this part in our material the first time around, after we finished talking about the kinematic equations, we did a little projectile motion first, but the next thing we talked about was force. And we discussed force in the context of forces being the thing that cause linear accelerations. So forces were measured in newtons, and they were the cause of the accelerations we'd been studying. And we will have an equivalent concept here. The rotational equivalent, or the sister variable to force, is something called a torque, which causes an angular acceleration. Exactly how torques cause angular accelerations we'll get to a little more next time when we talk about the rotational equivalent of Newton's second law. But for now, we just want to talk about torque in general, how we calculate it. Torque does have units of newtons times meters. That is mathematically equivalent to a joule, but you won't see torques listed in newtons in joules. You will always see them listed in newtons per meter, or the equivalent American unit, foot-pounds. So the equation for torque is torque, which is represented by the lowercase Greek letter tau, equals r times f times sine of theta. So I want to discuss what we mean by r and f and sine of theta. So tau is the torque, but what are the rest of these variables? F is the magnitude of the force that is causing the torque. All torques are caused by forces, but the force and the torque are different things. So F is the force that is causing this torque. And then R is something called the lever arm. It is the distance between the axis of rotation and the location where the force is acting. Last but not least is theta, and you know from our discussions on work that I love to make sure you really understand what the theta in each of these equations means. So in this case, theta is the angle between the force and the lever arm. So if I were to draw a picture here, we could think about something like a door. So a door has the axle or the axis of rotation. Those are the hinges on the end of the door, and then the door itself is just one big slab that extends out from there. So if we have a force that is pushing in or pulling in this direction, that would be our force, and the magnitude of that force, the strength of that force in newtons, would be the value for F. Then R is the length of the lever arm. So that's the distance from the axis of rotation to the point where the force is acting. That distance is R, the lever arm. So if we take this distance R and we take this force F, we can then find the angle between the two of those, which will give us the torque. I find it helpful to extend the force and the lever arm out with kind of a dotted line to help me see what's going on here. Because the theta that we need here could be either of these angles. It could be this angle here, or it could be this angle here. And it turns out, thankfully for all of you, that either of these angles will work. Technically, R is a vector, and technically, like we do in the work equation, we would connect these vectors tail to tail, and we would need the angle between them, theta. But it turns out that this other angle, the one over here, would work just as well, because the sine of those two angles is going to be the same. So that's the basic idea, the definition of torque, and how we find it. Eventually, we'll start to think about torques as either positive or negative with our usual coordinate system for rotation stuff. Counterclockwise is positive. And we'll think about whether the torque exerted by that force is trying to rotate the object clockwise or counterclockwise. So for the example of the force acting on the door, we would have a torque that is in the clockwise direction. So the force we have here acting on the door is trying to make the door rotate clockwise. And clockwise is the negative direction, so this would be a negative torque, but that won't turn out to be too terribly important until next time. So let's do a couple of example equations or example situations, clicker questions, to help us understand a couple of these variables. And I'm going to consider these in the context of trying to rotate a bolt with a wrench. So here we have our wrench, and I want to consider 3 different 50 Newton forces that we could apply to that wrench to try to turn the bolt. We could apply 50 Newtons onto the wrench at this point here, or at different points along the handle, but they're all going to be 50 Newton forces. So my question for you is, which of these forces is most likely to cause the bolt to rotate? So in other words, which of these forces exerts the greatest torque? So pause the video, think about it, and when we come back, we will see which of these is the correct answer and why. Hopefully you were able to find yourself an answer, and you might be able to answer this one just from personal experience, that you're going to have the best luck with the green force of 50 newtons. That will exert the largest torque. So what's the difference here? The difference here is the different lever arms. All of the forces have the same magnitude of the force. All of them are exerted at the same theta, perpendicular to the lever arm, so theta is 90 degrees. But they're different distances from the axis of rotation. So this distance right here would be the lever arm for the green rightmost arrow, the green rightmost force. And this distance here would be the lever arm for the blue force. Always the lever arm is the distance between the axis of rotation, in this case the center of the bolt, and the point where the force is acting. So this means that since the forces are the same, but green has a longer lever arm, the green force will exert more torque and be more likely to cause the bolt to rotate. So the further from the axis of rotation you push, the more torque that same force will create. I also want to point out that that red force is applied directly at the axis of rotation. So for that red force, the lever arm is 0, which tells us the torque caused by that red force will also be 0. So a force applied directly to the axis of rotation, either pushing directly on it or pulling directly on it, will result in no torque. So all torques may be caused by forces, but not all forces will cause a torque. There are ways to push and pull on something that does not cause it to rotate. So that's giving us a little more insight about what the lever arm is and how it can affect the torques that you calculate. Now let's try something different so we can think about the angle theta in this equation. And I'm going to couch this one in terms of the same type of wrench problem. And again, I'm going to have 3 different forces, all with the same amount of torque. The same amount of force. This 50 Newton force in red, directed perpendicularly to the wrench. We will have a 50 Newton force in blue that is directed kind of diagonally from the end of the wrench. And we will have a 50 Newton force in green that is directed along the axis of the wrench. So again, all of these forces have the same magnitude, and now they're all going to have the same lever arm as well. The lever arm here for all of these forces will be the distance from the location where the force is acting to the location where the axis of rotation is. So from the bolt to the end of the wrench, which is the location each of these forces are acting. So this distance is r in orange. And the question I want to ask you is the same question as before. Which of these forces is most likely to cause the bolt to rotate? So as before, take the time to pause the video and see if you can figure out which answer is correct, and then unpause the video to check your work. So hopefully you've had a chance to take a peek at this one, and the correct answer here is that the red force is most likely to cause the bolt to rotate. The red force exerts the largest amount of torque. So the difference here isn't the magnitude of the force. A stronger force causes a stronger torque, but they're all 50 newtons. It's also not the lever arm, because all of the forces are applied at the same distance away from the axis of rotation. The difference here is the angle at which the force is applied, which is theta in our equation. So to show you what the different thetas we have here look like, I'm going to kind of draw this same situation 3 different times, where we will have r each of the 3 times, and then we will look at which value we need for theta in each of these cases. The red force acts over here at the right end of the lever arm, pointing straight upward. So if we do what I did before and kind of extend both of our force and our lever arm with dotted lines, we would need any of these angles. Either this angle right here as theta or this angle right here as theta. In this case, our theta will be 90 degrees. And sine of theta will equal 1. So when the force is applied perpendicularly to the lever arm, we get the maximum possible torque. If we look at this same process for the blue force, the blue force is directed this direction, kind of up and to the right. So if we follow that same approach and extend with dotted lines both our force and the lever arm, we could get either of these two angles here, either this theta or this theta. Technically, the one on the right is the one we actually want, but either one will give you the same answer. Drawing myself some lines to separate this. Here, we'll have a value for sine of theta that's greater than 0, but is less than 1. So the torque is not 0. We will have some torque. This bolt might rotate, but this is an inefficient way to apply our force. And then last but not least, we have this green force, which is applied along the lever arm. So if we extend out our force and we extend out our lever arm in either direction, the angle between these is either 0 degrees or 180 degrees. And if theta is 0 or 180 degrees, that means sine of theta is 0, so the torque is also 0. And this is basically telling us that a force directed either directly toward the axis of rotation or directly away from the axis of rotation will cause no torque. So this would be like coming to our door over here and pushing directly along the axis of the door straight towards the axis, or pulling directly this way, straight away from the axis. Those forces exist, but they aren't going to cause the door to rotate, so they exert no torque on the door. So these are the two main effects, other than the strength of the force, that affect the torque that force causes. The length of the lever arm and the angle at which the force is applied. And for either the angle or the lever arm, we can apply a force in such a way that it exerts no torque at all. So all torques are caused by forces, but not all forces will create a torque. So I want to give you an example calculation that we can work our way through, and to think about a couple of other ways that we can think about this torque equation. And then that will be everything for today. So I want to consider that same door that we were talking about before, and two forces that we could possibly exert on that door. One force, a 30 Newton force applied perpendicularly to the door at a distance of 0.4 meters from the hinges, or the other force applied at some angle, where I'm going to say this angle right here is equal to 30 degrees. Too many 30s in this problem, but that's okay. Is equal to 30 degrees and is applied at a distance of 0.8 meters from the end of the door. So the question I want you to try to answer here is, which of these forces exerts a greater torque on the door? So is torque A greater than torque B, less than torque B, or are the torques equal? Pause the video and give yourself a second to work through this problem and try to determine the answer yourself. So, hopefully you've actually taken the time to do a calculation here. So let's figure this out. First, let's find the torque caused by force A. That will be Fr cosine theta. So force A times Ra times cosine theta A. You could just write Fr cosine theta, but we have two different forces applied at two different lever arms and two different angles. So I'm putting the A subscripts on there just to make it clear which ones I'm talking about. The lever arm for this first force is the distance from the axis of rotation to the force that is acting. So this distance right here is Ra, which is 0.4 meters. And the angle we need here is the angle between the lever arm and the force. So this angle right here is theta A, which is 90 degrees. So if we plug that in, torque caused by force A is the 30 newtons. That's the magnitude of the force of force A. No need to consider direction, just a magnitude. And that lever arm is this 0.4 meters. And I made a mistake. This should be a sine, not a cosine. My apologies. Times the sine of our angle, which is 90 degrees for this one. And if we plug all of that in to our calculators, we end up with an answer of 12 Newton meters worth of torque for force A. For force B, I'm going to go over this one in red and blue here so that I can do my math in a different color. To find the torque exerted by force B, we want the magnitude of force B, the lever arm at which this force acts, times the sine of the angle, whichever one we need. So for B, our lever arm will be the distance from the axis of rotation to wherever the force is acting. So this distance in light blue is RB, and that is the 0.8 meters. If we extend out our lever arm and we extend out our force along the lines that they act on, we can see that the 30 degrees here is the angle that we need. So that 30 degrees here is theta B. So nothing fancy, just plugging in some of the numbers we've been given. So torque B is equal to that 30 newtons of force, that's the magnitude of force B, times the length of the lever arm, 0.8 meters, times the sine of our angle here, which is 30 degrees. You also could have used 150 degrees, and you'd get the same answer. So once we plug this into our calculators, we get also 12 newtons per meter, newtons times meters. So both of these forces are exerting the same torque. It's not because they're both 30 newtons, because they both have different lever arms and they both have different angles. Force B has the longer lever arm, but force A has the more efficient angle at which that force is applied to create a torque. So those two effects effectively cancel each other out on this problem. Last but not least, I just want to go over some different ways to think about this equation. Torque equals Fr sine of theta. And to give us a situation to discuss, let's again consider this door on its hinges. And I want to think about the force applied at the very end of the door at an angle like this. So this is the force that we're going to be considering, and I'll give it a specific angle that we have from the axis here. So whatever this angle is, that would be given to you as theta. You can just plug in F and R and sine of theta if you want to. I will label the lever arm here on this problem in green, from the axis of rotation to the location where the force is acting. So this green line, the entire length of the door here, is the lever arm in this case. If we want, we can rearrange this torque equation by combining F and sine of theta into one term. So we could rewrite our torque equation as what's called the perpendicular force times the lever arm. And that perpendicular force is just the whole magnitude of the force times the sine of theta. So why would we want to think about our torque this way? And I can show you what I mean here. So if we think about this force, we could break this force down into components. We would have one component of this force that acts along the axis of the lever arm. We could call this the parallel component of the force. And that would be equal to F cosine theta. And we could find that component of the force, but this component of the force is directed directly toward the axis of rotation, or directly away from the axis of rotation. So because the parallel component of the force is in that direction, it will cause no torque. On the other hand, we also have another component to this force here that I will draw in orange. And that would be what's called F perpendicular, the component of the force that is perpendicular to the lever arm. And this is our F sine theta that shows up in that equation. And we would call this F perpendicular. And this force, the perpendicular component of the force, is perpendicular to the lever arm. So if we thought of just that component of the force, it would have a theta of 90 degrees, which would mean sine of theta is 1. So instead of just plugging into F times R times sine of theta, if we want to, we can think about the component of that force that is actually exerting a torque, which is the component that is perpendicular to the lever arm, or F sine theta. That can be a helpful way to think about things sometimes. The other way we can think about our FR sine theta equation is to combine R and sine of theta together. So we get torque is equal to F times R perpendicular, where, like before, the R perpendicular is just combining the R and the sine of theta into one term. So to show you what this means, I need to draw another picture. So what R perpendicular is if we go back to that same idea of extending out our force with a dotted line. So I call this the line of action of the force. So that line of action of the force tells us basically what axis that force is directed along. And in this case, the perpendicular lever arm is just this side of our triangle right here, our perpendicular, where this angle right here would be 90 degrees, and this angle here would be theta. So you can see with that right triangle that R times the sine of theta would give you the perpendicular lever arm. The perpendicular lever arm is just the closest the line of action of the force gets to the axis of rotation. This can be helpful if we have a situation where a more two-dimensional object is rotating. So if we have some rectangle that we have put an axis through the center of, we could think about applying a force to this corner directed downwards, say 50 newtons again. And we could think about applying a force to this corner in the upper right. We could also think of exerting another 50 Newton force here, up at the top. So these two forces have different values for R. From the axis to the 50 Newton force would be the R for this particular force, and then the distance from the axis of rotation, I'll do this one in light blue, to the orange force would be that value for R. But if we end up taking R times the sine of theta, then we get the perpendicular lever arm. So if we extend out that orange force with a dotted line, then R perpendicular will be the closest that dotted line gets to the axis of rotation. So that would end up being this distance here would be R perpendicular, which is the same as the R or the lever arm for the red force. So even though these two forces are applied at different distances from the axis of rotation, and even though the forces would have different values for theta in their equations, because the red force is perpendicular to its lever arm, but the orange force is not perpendicular to its lever arm. We can still see that these two forces exert the same torque by thinking about the perpendicular lever arm. So these other two ways of calculating the torque can be helpful, and they can be useful for thinking through problems, especially problems where they feel like they don't give you all of the information you need. But ultimately, if you just want to plug in to FR sine theta, that will pretty much always work. So thank you all for putting up with me through this unanticipated video that I did not plan to end up making today, but I wanted to make sure we keep everything on schedule, and this will allow us to do that. Thank you for watching, and have a good day.